Hello, I'm Miss Legg-Battles, and I'm here today to talk to you about law of sines. Now, in our discussion of sine and cosine and tangent, have you ever wondered why we only had right triangles that only apply to right triangles? Well, today we're going to use law of sines, and it's going to apply to triangles like the one in the picture here, where it's not a right triangle. So today we're going to talk about when we're going to use law of sines, we're going to derive the law of sines, and we're going to look at a couple of examples using the law of sines. Hoo-hoo for the law of sines. Okay, first of all, when are we going to use the law of sines? Well, in a triangle, if we are given two angles and a side, like remember our congruence patterns, like angle, angle, side. If we knew two pairs of angles and a pair of sides were congruent, then we knew that the triangles were congruent. That's because it defines the size of the triangle. So if we have angle, angle, side, or angle, side, angle. So if we know two pairs of angles and one pair of sides, we're going to use law of sines. Now, it will also work in the dreaded side-side angle, provided that that angle is obtuse. Now, if the angle is not obtuse, that's what we call the ambiguous case, where there could be two different possible triangles. And so if this angle is acute, there are two different sets of answers that we could have in the ambiguous case. So for now, we're just going to look at it when this angle is obtuse. Now we're going to derive the law of sines. So I have my original diagram here, but I've dropped in an altitude, h, and that has given me two right triangles. Now that I have right triangles, I know that my right triangle definitions to the trig functions apply. So I'm going to use them to write an equation here. Sine of A equals, now sine is opposite over hypotenuse, so that would be H over B. Likewise, over here, I would have sine of B. Sine of B, sine is opposite over hypotenuse, so that would be H over A. And since I have H in both equations, I'm going to solve for H. So I'm going to multiply both sides by B here, and the b's will divide out. So when I do that, I'm left with b sine of A equals H. Over here, I'm going to multiply both sides by A. And the A's divide out here, and I have it solved for H. So A sine of B equals H. Now, as we continue on here, I want you to notice the difference in my capital letters and my lowercase letters. Often I see students use those interchangeably, and they represent different things. The lowercase b right here, it represents the length of the side in this triangle that's opposite from angle B. The capital B represents an angle, lowercase b is the side opposite from angle B. Same thing with A. Lowercase a represents the length of the side that's opposite capital A in my original big triangle. So notice now that I have two different expressions that represent H. Both of these are equal to H, and if that's the case, then they must be equal to each other. So B sine of A must be equal to A sine of B. Now, to get it in a little different form, I'm going to divide both sides by AB. Lowercase a, lowercase b. And here the b's will divide out, and here the a's will divide out. And look at what it leaves me with. It's really quite nice. Leaves me with sine of a over lowercase a, this is the side opposite from angle A, equals sine of b over lowercase b. And this is the law of sines. Now, I can extend that to also be true for angle C and lowercase c. Remember, C is not a right angle anymore. When we used it for just right triangles, C was a right angle. But now, the original triangle is not a right triangle. So it also worked for C. So I can extend law of sines to this. So I have the same thing I just added, sine of C over C. Remember, lowercase c is the length of the side that's opposite from angle C. And I think as we look at some examples, you're going to see how that works. Ready for some examples? Awesome. Okay. This says, in triangle ABC, measure of angle A is 70, measure of angle C is 62, BC. Remember what BC means? The length of segment BC is 7.3. So to the nearest tenth, we're supposed to find AB. Again, that means the length of segment AB. So let's label our diagram. Measure of angle A is 70. Measure of angle C is 62. BC is 7.3. Now remember when we were going to use law of sines? Anytime we have two angle measures and one side. This is an angle-angle side pattern. It doesn't matter as long as you have two angles and one side. Law of sines is going to apply. So let's write an equation for that. Now, look at this BC right here. In my formula, what was BC? BC is the side opposite angle A, so it was lowercase a. And AB that we're looking for right here, AB, that is opposite from capital C, which would be lowercase c. So I'm going to write them that way so it will match up with the way I wrote my formula. So let's write our equation. We have the A's and the C part, so that's the part of the law of sines I need. Sine of A over lowercase a equals sine of C over lowercase c. So let's plug in. Sine of A, the measure of angle A was 70 degrees. Over lowercase a. Lowercase a, remember that's opposite from capital A, so that's my 7.3. Equals sine of C, which is sine of 62 degrees, over lowercase c, which remember that's what I'm looking for because capital A, capital B is the length of segment AB, which is lowercase c because it's opposite from angle C. Now, we have a proportion. So how are we going to solve our proportion? Cross multiply. So that gives me C sine of 70 equals 7.3 times sine of 62. Now, when we have a length like this multiplied by the sine of an angle measure, we're always going to put that in the front, just like we did the problems in the last section. Because if we put it after 62, it could look like we're multiplying 62 degrees by 7.3 instead of 7.3 times sine of 62 degrees. Now, to solve for C, we need to get rid of that sine of 70. So we're going to divide both sides by sine of 70. Now, you have your calculators ready? We're going to put this in our calculator. These will divide out, and we're left with C is equal to 7.3 times sine of 62 divided by sine of 70. Now, let me caution you about an error that students sometimes make when entering this in their calculator. They'll put in 7.3 sine of 62 divided by sine of 70 without closing the parentheses that the calculator puts in there. And when you do that, it's only going to divide the 62 by sine of 70 instead of this whole value. So you need to check your calculator now and make sure you get what I get. If you put in 7.3 sine of 62 divided by sine of 70, you should get 6.9. 6.9. Ooh. While you're checking on your calculator, let me write it neater. Okay, the next problem that I have for you says to use the law of sines to find the values of x and y, and we're going to round to the nearest tenth just like we did on the previous problem. Now, I like this problem. It's not labeled like the previous one, A, B, and C. Doesn't have anything labeled. But we know the things that go together. When we take sine of 63, that goes with, what's the side length opposite from angle 63? That's 18. And that's why I chose those, because I know an angle measure and I know the side length that's opposite from it. So if I want to solve for x, I'm going to have to use the angle that's opposite from x. So that would be sine of 71 over x. See, I didn't have the A's, B's, and C's this time, but it doesn't matter. What matters is that this 63-degree angle is opposite the side length 18, and this 71-degree angle is opposite from x. So again, we have a proportion, so we can cross multiply and solve for x. So that's going to give me x sine of 63. Remember, I'm putting that length in the front, equals 18 times sine of 71. Now, to get x by itself, I'm going to divide both sides by sine of 63. These will divide out, and I'm left with x equals this, 18 sine of 71 divided by sine of 63. So we're going to put it in our calculator and round that off to the nearest tenth. Okay, I'll give you just a minute to put that in your calculator. Remember, when you put in 18 sine of 71, it's going to open parentheses there in front of 71. Close them, so it will compute that, and then divide by sine of 63, and you should get 19.1. Okay, now we're going to need to solve for y, right here. Now, to solve for y, I can use the same first part of my proportion, this same ratio here, sine of 63 over 18. But for this part, if I'm looking for y, I have to know this angle measure right here. Okay? Do we know that angle measure? How about the triangle angle sum theorem? Okay? The triangle angle sum theorem says 180 minus 63 minus 71 is going to give me 46. So this angle that's opposite from y would be 46 degrees. So this would be sine of 46. See, if you know two angles of a triangle, you can always very easily find the third angle using the good old triangle angle sum theorem. So now I have my proportion, and I'm going to cross multiply. Now, why don't you see if you can finish this and get it in your calculator before I get to that. That'll be cross multiplying. I'll get y times sine of 63 equals 18 times sine of 46 and then I'm going to divide both sides by sine of 63 to get y by itself. Okay, the sine of 63, those divide out, and I'm left with y equals 18 sine of 46 over sine of 63. So let's put that in our calculator and round to the nearest tenth. And dramatic pause. Everyone got 14.5. Yes, 14.5. Good. I have to say, my students were very cooperative today. Hoo-hoo, it has been a great day to me in geometry. I hope this video on law of sines will help you, and I know that you'll be able to use this a lot in your future math courses. Have a great day.